Welcome back to Cosmic Drift. Tonight our journey will not take us to distant galaxies or dying stars. Instead, we will return here home. We will travel back through deep time to a time before humanity, before the dinosaurs, before the first forests. We will go to a world that is alien, yet deeply familiar, the early Earth. And here on a barren rock orbiting a young sun, we will confront one of the biggest, deepest, and most elusive questions science has ever asked. A question that concerns all of us, our very existence. That question is, where do we come from? How did life begin? Let's recreate the scene. 4 billion years ago. The solar system was still a chaotic place. The Earth was an unrecognizable world. The sky might have been orange or red, veiled by a thick, oxygen-poor atmosphere full of carbon dioxide, nitrogen, and water vapor. Global oceans, perhaps an iron green, were churning under the impact of acid rain and a constant bombardment of asteroids and comets, the leftovers from the formation of the planets. The surface was a volcanic hellscape. Molten lava flowed across the young continents. There was not a single tree, not a blade of grass. Not a single creature swam in the oceans. There was no sound but the roar of thunder and the hiss of the wind. It was a sterile world, a barren rock made of simple inorganic chemicals. Now fast forward to today. Our planet is teeming with life in every corner. From the microbes surviving in the deepest hydrothermal vents at the bottom of the ocean, to the complex rainforests, to you yourself, an organism made of some 37 trillion cells each one, an astonishingly complex biochemical machine working in harmony. Inside each of those cells is an even more incredible molecule, DNA. A double helix, billions of characters long, carrying the detailed blueprint to build and operate your entire body. It is a biological supercomputer, a library of encrypted information. And here lies the greatest mystery of all. How did we get from point A to point B? How from a world of simple inorganic chemicals, rock, water, gas, did the universe manage to create something as complex, structured, and self-replicating as DNA? The leap from geology to biology, from non-living matter to living matter, is one of the great frontiers of modern science. This process is called abiogenesis. We have a few ideas. We know that the basic building blocks, simple organic molecules like amino acids, can be created naturally. The famous Miller-Urey experiment in 1952 proved that. They simulated the conditions of the early Earth in a flask with water, methane, ammonia, and hydrogen, and used electric sparks to simulate lightning. After just 1 week, they found amino acids had formed spontaneously. Later experiments have created all sorts of organic molecules necessary for life. It seems the primordial soup on early Earth truly had enough ingredients. But there is a huge gap between having the bricks and building a skyscraper. How did those individual amino acids link themselves together to form proteins? How did the nucleobases assemble themselves into chains of RNA and DNA capable of storing information and replicating themselves? This is an extremely thorny chicken and egg problem. DNA needs proteins to replicate, but the recipe to make the proteins is stored in the DNA. So which came first? Many scientists believe the answer lies in RNA, a molecule that can both store information and act as an enzyme. An RNA world may have preceded our DNA world. But even so, the probability of all this happening randomly in a vast ocean seems incredibly low. This has led some scientists to another question, a question that completely changes the perspective. What if some of the most complex steps didn't happen here? What if the Earth wasn't the place that had to manufacture all its own ingredients from scratch? What if we got a little help from the outside? This is where an alternative hypothesis, a fascinating possibility, enters the story. We are faced with one of the greatest mysteries, the leap from inorganic chemistry to complex biology. How did a barren planet become a living world? The first explanation in the mainstream view in science is a process called abiogenesis, a word of Greek origin, meaning not bio, meaning life, and genesis, meaning beginning. The beginning of life from non-living matter. This hypothesis suggests that everything needed for life was already here on the early Earth. And given enough time, energy, and the right conditions, life was not just possible, but an almost inevitable consequence of the laws of chemistry. The modern idea of abiogenesis began to take shape in the 1920s with the independent work of two scientists, Alexander Oparin in the Soviet Union and J.B.S. Haldane in Great Britain. They proposed that the early Earth's atmosphere was a reducing environment with no oxygen and rich in gases like methane, CH4, ammonia, NH3, and hydrogen, H2. They envisioned that under the influence of abundant energy sources, like lightning from perpetual storms, ultraviolet radiation from a young and active sun, and heat from volcanoes, these simple gases could have reacted with each other in the atmosphere. These reactions would have created simpler organic molecules, the first bricks. Then these molecules would have rained down into the early oceans, accumulating over millions of years, turning the oceans into a warm, nutrient-rich, primordial soup. In this soup, protected from the harsh UV radiation, the molecules could continue to react with each other, forming longer and more complex chains. This was a beautiful and logical idea, but for many years it remained just a hypothesis, until 1952, at the University of Chicago, a young graduate student named Stanley Miller, under the guidance of Nobel laureate chemist Harold Urey, decided to conduct one of the most daring and famous experiments in the history of science. They built a closed glass system to simulate the early Earth. At the bottom was a flask of boiling water simulating the primordial ocean. The water vapor rose and mixed with a cocktail of gases, methane, ammonia, and hydrogen simulating the atmosphere. Then they passed this gas mixture between two electrodes where electric sparks were continuously fired, simulating the ceaseless lightning storms. Finally, a condenser cooled the mixture, causing a rain containing the reaction products to fall back into the ocean. They let this experiment run for 1 week. The results exceeded all expectations. Initially, the water in the flask was colorless, but after a few days, it began to turn pink and then a deep red, a clear sign that complex chemical reactions were taking place. When Miller analyzed that red solution, he was astonished to find that it contained several types of amino acids. Amino acids are the fundamental building blocks of proteins, the molecular machines that do most of the work in our cells. The Miller-Urey experiment had proven eloquently that from simple inorganic chemicals and a source of energy, the organic building blocks of life can be created spontaneously. The first leap from inorganic to organic did not require a miracle. It was a natural consequence of chemistry. Since then, countless variations of this experiment have been performed using different gas mixtures and energy sources. Scientists have been able to create all 20 types of amino acids found in life. The nucleobases, the letters of DNA and RNA sugars, and lipids. The primordial soup seems to have had all the necessary ingredients. The abiogenesis hypothesis doesn't just stop at the oceans. Some scientists believe that life may have begun in more specific places, for example, in deep-sea hydrothermal vents. These black smokers spew out hot mineral and chemical-rich water, creating an environment with a large energy and chemical gradient, an ideal place for complex reactions. Or perhaps in small warm ponds on land where cycles of wetting and drying could have helped molecules polymerize into longer chains. Regardless of the exact location, the core idea of abiogenesis remains: the same life is a local phenomenon. It sprouted and evolved entirely here on our planet from the available materials. This is a powerful and well-supported viewpoint. But it still has large gaps, especially in the step from individual bricks to a first self-replicating structure. And it is these very gaps that leave room for another possibility, a possibility that doesn't deny abiogenesis, but simply proposes that some of the best ingredients may not have been homemade. The abiogenesis hypothesis has painted a powerful picture life emerging from the very materials available on the early Earth, a self-contained and independent process. But a question remains: were all the ingredients cooked at home, or did our primordial soup receive a few special ingredients delivered from elsewhere? This leads us to an alternative hypothesis, an idea that dates back to ancient Greece, but has only been seriously considered scientifically in the last century, an idea that is both simple and profound. What if life, or at least its seeds, didn't start here? What if they came from the stars? This is the panspermia hypothesis. Panspermia, a word of Greek origin, pan, meaning all, and spermia, meaning seed. Seeds everywhere. Its core idea is that life, or the components of life, are common in the universe and are spread from place to place. It does not solve the ultimate mystery of the origin of life, but it proposes that life on Earth may not be a unique event, but part of a larger cosmic process. This hypothesis has different versions with varying degrees of boldness. The strongest and most controversial version is called lithopanspermia. Litho means rock. This hypothesis suggests that actual living microorganisms like bacteria or extremophiles could survive an interstellar journey, trapped inside rocks, blasted off from a life-bearing planet by a major impact. These rock ships would travel through space for millions of years, and if they happened to land on another planet with suitable conditions, the microorganisms could awaken and start a new evolutionary chain. In this scenario, we could all be descendants of microbes from Mars or even from another star system. This is a fascinating idea, but it faces enormous challenges. Could life survive the initial impact, the harsh radiation of space, and the shock of atmospheric re-entry? Another version, called directed panspermia, is even more science fiction. It suggests that life was intentionally seeded on other planets by an advanced extraterrestrial civilization. This is an interesting idea to explore in stories, but it is completely outside the realm of testable science at the moment. And then we come to the third version, a softer, less controversial version, and most importantly, one that has more observational evidence to support it. It is called chemical panspermia, or sometimes pseudopanspermia. This hypothesis does not suggest that life itself is transported between the stars. It suggests that the building blocks of life are transported. It proposes that complex organic molecules, amino acids, nucleobases, lipids, are formed naturally and abundantly in various environments in the universe, such as in giant molecular clouds or on the surfaces of asteroids and comets. Then these delivery vehicles, especially comets and asteroids, would carry these chemical seeds and sow them on young planets like the early Earth. From this perspective, chemical panspermia is not an alternative to abiogenesis. It is a supplement. Life still emerges from inanimate matter right here on Earth. But that process was boosted, enriched by a continuous rain of complex organic molecules from space. Instead of having to create all the ingredients from scratch in a dilute soup, the early Earth received high-quality pre-made components delivered to its doorstep. This could have significantly increased the speed and probability of the next steps toward life occurring. This is an extremely powerful hypothesis because, unlike the other versions, we can test it. We can analyze meteorites. We can send spacecraft to comets. And we can observe interstellar visitors. And for our journey tonight, when we speak of the seeds of life, it is this version of chemical panspermia that we will explore. We will not be talking about traveling microbes. We will be talking about traveling carbon molecules. And our traveler, 3I Atlas, with its brilliant carbon signature, is one of the most compelling pieces of evidence that these chemical sowers are not just operating in our own backyard. We have laid out two possibilities for the origin of life sprouting entirely at home or being sown with chemical seeds from space. The chemical panspermia hypothesis, the idea of the building blocks of life being delivered by comets and asteroids, is a fascinating one. But science does not operate on fascinating ideas. It operates on evidence. So do we have any concrete evidence that objects from space actually carry these complex organic molecules? The answer is a resounding yes. And the first one of the most powerful pieces of evidence fell from the sky on a September morning in 1969. Chapter 2. Evidence in our own backyard. At around 10:58 a.m. on September 28, 1969, the residents of the small town of Murchison in Victoria, Australia, witnessed a spectacular sight. A brilliant fireball tore through the daytime sky, accompanied by a sonic boom that shook the ground. Then a rain of black, pungent-smelling stones fell over a wide area. This was no ordinary rain. These were the fragments of a meteorite that had just entered Earth's atmosphere. In total, over 100 kilos of cosmic rock was collected. This event, known as the Murchison meteorite, occurred at an extremely fortunate time. NASA's Apollo program was at its peak, and laboratories around the world were equipped with the most advanced analytical tools to study lunar rock samples. Immediately, scientists realized that the Murchison meteorite was a golden opportunity. It was a pristine sample from space delivered for free. And because it was collected so quickly after it fell, the risk of contamination by organic compounds on Earth was very low. This type of meteorite is classified as a carbonaceous chondrite, one of the most primitive and unaltered types of rock in the solar system. They are thought to be fragments of asteroids formed in the outer asteroid belt, where there was more ice and organic compounds. They are the leftover building blocks from 4.6 billion years ago. When scientists began to analyze the fragments of Murchison in their labs, they found a chemical treasure trove. Inside these black porous rocks, they discovered an incredible diversity of organic molecules. And the most important discovery was the detection of amino acids. They didn't just find one or two types. They identified over 100 different kinds of amino acids. Here's what's astonishing. Life on Earth uses only 20 standard types of amino acids to build all of its proteins. The Murchison meteorite contained some of those 20, like glycine and alanine, but it also contained over 80 other types, ones that are never found in earthly biology. They are exotic building blocks. The presence of these alien amino acids was irrefutable proof that they were not the result of contamination from Earth. They were truly formed in space inside the meteorite's parent asteroid. But how could they be even more certain? They looked at a subtle chemical property called chirality. Most amino acids exist in two enantiomeric forms, like your left and right hands. They are mirror images of each other. Curiously, life on Earth uses almost exclusively the left-handed form of amino acids. If the amino acids in the meteorite were from contamination from Earth, they would also be predominantly left-handed. But when scientists analyzed Murchison, they found a nearly equal mixture of both left and right-handed forms, a racemic mixture. This is characteristic of non-biological, naturally occurring chemical processes. The evidence was now solid. The Murchison meteorite was a chemical letter sent from the asteroid belt, and that letter said, "Amino acids, the bricks of life can be created naturally and abundantly in space." Besides amino acids, later analyses found nucleobases, adenine, guanine, the letters of DNA and RNA, along with sugars, alcohols, and a whole host of complex hydrocarbons. The Murchison meteorite had proven eloquently that the primordial soup didn't just exist on Earth. It existed throughout the solar system, and the reign of Murchison-like meteorites in Earth's early history could have played a crucial role in delivering the necessary ingredients for life to emerge. The Murchison meteorite gave us solid evidence from the asteroid belt. A letter written in stone proving that amino acids can form in space. But asteroids are only half the story. What about their icy cousins? Comets, the dirty snowballs from the cold outer reaches of the solar system, are thought to be even more primitive and richer in organic compounds than asteroids. To read their chemical letter, we can't wait for them to fall. We have to fly to them. And that is exactly what humanity did in one of the most daring and inspiring space missions ever undertaken. The Rosetta mission. Launched in 2004 by the European Space Agency, the Rosetta spacecraft began a 10-year, 6 billion kilometer journey through the solar system. Its mission sounded like science fiction, not just to fly by a comet, but to enter into orbit and travel with a comet as it approached the sun. And then to do something unprecedented, land a small probe on its surface. Its target was a comet with a rather difficult name, 67P Churyumov-Gerasimenko, an ice block shaped like a rubber duck about 4 kilometers wide. After a decade of flight using gravitational assists from Earth and Mars, Rosetta finally arrived at its rendezvous in August 2014. It had become the first artificial satellite of a comet. For the next 2 years, Rosetta flew alongside 67P, observing it in astonishing detail as it woke up. Rosetta was equipped with a suite of extremely sophisticated analytical tools. One of the most important was a mass spectrometer named Rosina. Rosina doesn't look at light, it sniffs. It could directly collect the gas molecules in the coma and analyze them with extraordinary precision, identifying each type of molecule one by one. And what it smelled confirmed and expanded upon what we had learned from Murchison. It found a veritable chemical zoo. Dozens of different organic molecules, from simple ones like formaldehyde to more complex ones. And then in 2016, after a careful data analysis process, the scientists announced a historic discovery. For the first time, they had definitively detected the presence of glycine in the comet's coma. Glycine is the simplest amino acid, but it is still an amino acid, one of the 20 building blocks used by life on Earth to build proteins. Furthermore, they also found phosphorus. Phosphorus is a critically important but relatively rare element. It is the central component of the ATP molecule, the energy currency of the cell. And most importantly, it forms the backbone of the DNA and RNA helices. Without phosphorus, there would be no DNA. There would be no heredity. Finding both glycine and phosphorus at the same time in the same comet was a monumental discovery. It showed that not just amino acids, but other key components of the biological machinery could also be formed in space and carried by comets. Rosetta had proven that comets are not just dirty snowballs. They are chemical delivery trucks carrying a starter kit for life. And the mission had one more climax. In November 2014, Rosetta released its small lander Philae onto the comet's surface. Although the landing was troubled, and Philae bounced several times before coming to rest in a shaded location, it still managed to perform the first ever analyses directly on the surface of a comet. The data from Philae combined with the data from Rosetta painted a complete picture. The Murchison meteorite had shown us what was in the asteroids, and Rosetta had shown us what was in the comets. Both told the same story: the basic components of life are not rare. They are common in our own backyard. We have seen that asteroids and comets are efficient delivery vehicles for organic molecules, the building blocks of life. But there is another ingredient, an even more fundamental and important one, without which the primordial soup could not exist. That is the very solvent of life, water. Earth's oceans cover over 70% of the planet's surface. They are the cradle of life. But where did that water come from? The answer seems obvious: it was always here. But the real story may be much more complex and much more cosmic. When the Earth formed about 4.6 billion years ago, it was a molten ball of rock. The inner region of the solar system was too hot for water ice to condense. So the early Earth may have been born relatively dry. So how did we get the massive oceans we have today? A leading hypothesis is that most of the Earth's water was delivered later during a period known as the Late Heavy Bombardment, about 4.1 to 3.8 billion years ago. During this chaotic period, as we know, the migration of the giant planets stirred up the asteroid and comet belts, throwing a huge number of icy bodies into the inner solar system. The early Earth was subjected to a relentless rain of these snowballs. And each comet, each water-rich asteroid upon impact, released a large amount of water vapor into the young Earth's atmosphere. Over millions of years, this vapor condensed and fell as rain, slowly filling the ocean basins. This is a very plausible idea. But how can we test it? We can't go back in time. The answer, once again, lies in chemistry, in a subtle fingerprint hidden within the water molecules themselves. Water, as we know, has the formula H2O, 2 hydrogen atoms and 1 oxygen atom. But hydrogen is not just one type. Most of the hydrogen in the universe is normal hydrogen with just a single proton in its nucleus. However, there is a rarer, heavier isotope called deuterium, or heavy hydrogen. Its nucleus contains 1 proton and 1 neutron. Water made from deuterium HDO is slightly heavier than normal water H2O. By measuring the DH ratio, that is the ratio of deuterium to normal hydrogen in a water sample, scientists can get a unique isotopic fingerprint. And here's the key. The DH ratio is not the same everywhere in the solar system. It depends on the temperature and conditions where the water was formed. Generally, water that formed in colder regions farther from the sun tends to have a higher DH ratio. So the test is clear. If Earth's oceans were formed from a rain of comets and asteroids, then the DH ratio in our seawater must match the DH ratio of those objects. Scientists got to measuring. They measured the DH ratio in Earth's oceans and got a standard value. Then they started measuring the DH ratio in comets. The initial results were puzzling. The first comets measured coming from the distant Oort cloud had a DH ratio twice as high as Earth's seawater. This suggested they could not be the main source of our water. But then the Rosetta mission brought a key discovery. Comet 67P, a comet from the Kuiper Belt, a region closer than the Oort cloud, had a ratio that was 3 times higher. However, observations of other Kuiper Belt comets like Comet Hartley 2 showed a DH ratio that was a near-perfect match for Earth's water. And more recently, scientists have analyzed carbonaceous chondrite meteorites, the fragments of water-rich asteroids from the outer asteroid belt. And they have found that the DH ratio of the water trapped inside these rocks is a stunningly good match for the water in our oceans. The current picture, though still being debated, seems to be this Earth's oceans did not come from a single source. They are a mixture. The majority may have come from water-rich asteroids from the outer belt, and a smaller portion may have been contributed by comets, especially those from the Kuiper Belt. The evidence in our own backyard has become clear. Comets and asteroids didn't just bring the bricks, they also brought the water to mix the mortar. They provided both the solvent and the solutes for the primordial soup. In our own backyard, the evidence has become clear. The Murchison meteorite, the Rosetta mission, and the isotopic analysis of water all tell the same story. The asteroids and comets in our solar system are efficient reservoirs and transporters for the basic components of life. They sowed chemical seeds on the early Earth, but that is just the local story. It only tells us what happened here. To truly understand the potential of chemical panspermia, we must expand our perspective. We must look beyond the borders of our solar system. We must build a bridge between the stars. Chapter 3. The bridge between the stars. The core argument for expanding panspermia to an interstellar scale is based on a foundational principle of science known as the Copernican principle, or the principle of mediocrity. This principle states that Earth is not a special or privileged place in the universe. Our sun is just an ordinary star in an ordinary galaxy. Therefore, the laws of physics and chemistry that operate here must also operate everywhere else in the universe. Let's apply this principle to our story. We have seen that complex organic molecules can form in the environment of the early solar system and become trapped in comets and asteroids. So, is there any reason to believe that this process is unique to our solar system? The answer is absolutely not. The basic ingredients, hydrogen, helium, carbon, oxygen, nitrogen, are common throughout the Milky Way. They are the raw materials available everywhere. And the process of star formation, which is also the process of forming protoplanetary disks, is a universal phenomenon. The Hubble and James Webb telescopes have captured images of countless star nurseries and dusty disks orbiting other young stars. The laws of chemistry, the reactions that create organic molecules from simpler elements, also work in the same way whether they are here or 500 light years away. In fact, radio telescopes have detected the fingerprints of hundreds of different types of organic molecules, including very complex ones floating freely in the giant gas clouds between the stars, the very places where future stars and planets will be formed. Therefore, the logic is undeniable. If the comets and asteroids formed in our solar system are full of organic compounds, then the comets and asteroids formed in the billions of other star systems across the Milky Way must be as well. The primordial soup wasn't just cooked here. It is being cooked in billions of other cosmic kitchens. Every young star system is a factory for producing the building blocks of life. This truth on its own is already profound. But it would mean nothing for panspermia if those bricks were permanently trapped in their home star systems. For panspermia to work on a galactic scale, there must be a transport mechanism, a way to export these chemical seeds from one star system and import them into another. And as we have explored in previous journeys, that mechanism not only exists, it is extremely common. It is the process of dynamical instability in early planetary systems. The chaotic dance of giant planets, the gravitational slingshot effect, is not a phenomenon that only happened here. It is an almost mandatory phase in the evolution of most planetary systems. Every young star system is not just a comet factory. It is also an efficient comet launcher, constantly throwing billions, trillions of icy capsules into the common space of the galaxy. And so, the bridge is built, a bridge between the stars made of a relentless flow of icy travelers. Each of these travelers is a message in a bottle thrown from a distant shore, and inside each bottle is the potential for the chemical ingredients of life. We have established a solid logic. The chemical factories producing the building blocks of life operate throughout the galaxy, and the mechanisms to transport those building blocks between the stars are also common. When we combine these two truths, a new astonishing picture of our Milky Way begins to emerge. The space between the stars is not an empty, dead place. It is an ocean, a bustling ocean filled with potential delivery vehicles. It is the Sea of Exiles. Let's try to visualize the scale of this phenomenon. Our Milky Way has some 200 to 400 billion stars. Let's assume conservatively that a quarter of them, about 50 billion, have formed planetary systems and comet belts similar to our own. Now, consider the solar system. Scientists estimate that our Oort cloud contains about 1 trillion comets. And during the early instability phase, a number of comets, perhaps 10 to 100 times larger, were completely ejected from the solar system. Let's take a modest number of 10 trillion comets ejected from a single star system. Now let's scale that up. 50 billion star systems, multiplied by 10 trillion exiles from each. The final number is almost incomprehensible. 5 times 10 to the 23rd power, that is 500 sextillion. That is the estimated number of interstellar objects of homeless comets and asteroids wandering the Milky Way right now. That number is trillions of times larger than the number of stars in our galaxy. The space between the stars is truly a sea of exiles. They form a vast, invisible population, a dark matter of small bodies. They do not drift randomly. They follow the grand gravitational currents of the galaxy, influenced by the spiral arms and magnetic fields. The Milky Way has its own rivers, and these exiles are the sediment flowing in that current. And here's the core idea. If a significant fraction of these quadrillions of travelers are supercharged with organic molecules, then the Milky Way is not just a place of material exchange. It is a place of biological potential exchange. There is a giant invisible chemical river constantly flowing through the galaxy, carrying the seeds of life from one place to another. What does this mean for Earth? It means the chemical rain that seeded our planet may not have just come from our neighbors in the solar system. Throughout its 4.5 billion year history, the Earth has passed through countless of these interstellar rivers. We have been subjected to a rain not just of local comets, but of visitors from thousands, millions of different star systems. Our primordial soup may have been enriched by chemical spices from all over the galaxy. The existence of this sea of exiles makes the chemical panspermia hypothesis extremely compelling. It provides a large-scale, efficient, and continuous transport mechanism. It transforms a speculative idea into an almost statistical inevitability. And it is in this grand context that the arrival of 3I Atlas became an iconic moment. It was no longer just a strange point of light. It was our first tangible evidence of a member of that invisible nation. We have pictured a living Milky Way, a bustling sea of exiles of potential carriers for the chemical seeds of life. This is a grand idea built on statistical models and the laws of physics, but until recently it was just an idea. We needed proof. We needed to catch one of these carriers in the act. And then 3I Atlas arrived. It was no longer just a comet. It had become an exhibit, a perfect example, a proof A, for the hypothesis of galaxy-scale chemical panspermia. Let us together look once more at the portrait of this carrier. To be considered an effective interstellar carrier for chemical seeds, an object needs to meet 3 core criteria. First, it must truly come from another star system. 3I Atlas meets this criterion perfectly. Its extremely hyperbolic orbit is irrefutable proof. It is not a member of the solar system family. It is a true tourist having crossed the ocean between the stars to get here. It confirmed that the bridge between the stars is real. Second, it must contain the necessary cargo. That is complex organic molecules, the building blocks of life. And this is where 3I Atlas shines most brightly, quite literally. Its chemical signature expressed through its spectacular blue color was a cosmic neon sign, signaling an abundance of carbon. It screamed, "I am rich in organic compounds." This abundance, as we have speculated, is very likely the legacy of a red dwarf homeland, a gentler chemical environment that allowed these molecules to accumulate. 3I Atlas proved that comets from other star systems not only exist, but they can be supercharged with the precursors of life, perhaps even more so than our own comets. It was a carrier with a high-quality cargo hold. And third, it must be able to protect that cargo during the long journey. The billion-year journey of Atlas through interstellar space was a harsh ordeal. It faced eternal cold and a relentless rain of high-energy cosmic rays. But the structure of a comet is a perfect transport vessel. Its icy core wrapped in a dark organic crust, forged by radiation acts as a natural shield. Just a few meters of outer ice is enough to completely protect the complex and fragile organic molecules deep inside from the ravages of space. It is not just a ship. It is an armored ship, a cryogenic vault traveling between the stars. So 3I Atlas checked all the boxes. It was a confirmed carrier. It carried a high-quality cargo, and it was equipped to protect that cargo over unimaginable distances. It is a perfect example, a poster child for the chemical panspermia hypothesis. Its arrival transformed a speculative idea into a tangible, observable possibility. It showed us that the chemical river of the galaxy is real, and we have just seen one of the boats floating on that river. This does not mean that 3I Atlas seeded life on Earth. It just passed us by, but it shows that the billions of its siblings, those who came before it in the early history of the solar system, could have done just that. 3I Atlas was not just a comet. It was a piece of evidence, a crucial piece in our greatest puzzle. It was a whisper from the cosmos saying that life on Earth may not be an entirely local story. It may be a story with origins among the stars. We have identified 3I Atlas as a perfect interstellar carrier, a living proof for the chemical panspermia hypothesis. It is an armored ship carrying a precious cargo. But what exactly did that cargo hold contain? By observing from a distance, we can only see what is released, the final products of the chemical factory in the coma. We have seen the brilliant signature of dicarbon, but dicarbon is just the smoke. And where there's smoke, there must be fire. In this chapter, we will use that smoke to infer the fire within. We will open the cargo hold of Atlas. Chapter 4. The Organic Cargo Hold of Atlas. The extremely strong dicarbon C2 signature in the spectrum of Atlas is our most important clue. Recall that dicarbon is not an original component of cometary ice. It is a secondary product, a child born from the breakdown of more complex organic parent molecules by the sun's ultraviolet light. The logic here is simple. To have a large amount of the final product, dicarbon, you must start with a huge amount of the raw materials, the parent molecules. The brilliant blue of Atlas doesn't just tell us there is dicarbon. It tells us that its nucleus must contain an extremely high proportion of volatile organic compounds. So what could those parent molecules be? Based on our knowledge of astrochemistry and what has been observed in other comets, scientists can draw up a list of the main suspects. Suspect number 1, methane CH4. This is the simplest hydrocarbon, one carbon atom bonded to 4 hydrogen atoms. It is the main component of natural gas on Earth and is thought to be extremely common in the molecular clouds where stars and planets form. Methane is an efficient source of carbon, and its photodissociation can create the necessary free radicals for the formation of dicarbon. Suspect number 2, acetylene C2H2. This molecule is even more interesting. It contains 2 carbon atoms already bonded together. When UV light breaks the weaker hydrogen bonds, the C2 skeleton can be easily released to form dicarbon. Acetylene is considered one of the most direct and efficient precursors to dicarbon in the cometary environment. Its abundance in the ice of Atlas could be one of the main reasons for its brilliant blue. Suspect number 3, ethane C2H6. Similar to acetylene, ethane is also a hydrocarbon containing 2 carbon atoms. It is also a potential source of dicarbon. The presence of these simple parent molecules is almost certain, but the cargo hold of Atlas may have contained things much more complex. Scientists also believe that cometary ice contains polycyclic aromatic hydrocarbons, PAHs. These are large, flat molecules made of fused benzene rings, like molecular-level honeycombs. They are thought to be one of the most common forms of organic carbon in interstellar space. In addition, there are alcohols like methanol, CH3OH, and aldehydes like formaldehyde, H2CO. Formaldehyde is particularly important as it can participate in reactions to form ribose, the sugar that makes up the backbone of RNA. All of these molecules, methane, acetylene, ethane, PAHs, methanol, formaldehyde, are organic bricks, and they all have one thing in common. They are made of the elements of life: carbon, hydrogen, oxygen, and nitrogen. The con elements, 3I, Atlas, as it traveled through the solar system, was like a cosmic grocery store carrying all the basic ingredients needed to start a complex chemical recipe. This is not just speculation. Although we could not see these parent molecules directly in Atlas, their presence in other comets has been confirmed. The Rosetta mission detected a whole suite of organic compounds in Comet 67P. Radio telescopes like ALMA have also detected complex organic molecules in other comets as they approach the Sun. Therefore, inferring that Atlas also contained a similar and perhaps even richer cargo hold is perfectly scientifically sound. The blue smoke of decarbon has clearly shown us that the fire of organic chemistry inside the nucleus of Atlas was burning very brightly. It was not just a carrier. It was a carrier that was fully loaded. We have opened the organic cargo hold of 3I Atlas, a rich collection of carbon-based molecules, the potential precursors to life. But these molecules, as important as they are only the solutes. To have a soup, you need a solvent. And in the universe, the most common and powerful solvent, the liquid of life, is water. Although we have focused on the carbon legacy of Atlas, we must not forget that its main component, like most comets, was still water ice. And the role of this ice was not just structural. It was a protector, a nurturer, and a frozen prison. When 3I Atlas was formed in the protoplanetary disk, water, H2O molecules, were the most abundant ice available. They crystallized together, forming a porous structure like a giant crystal lattice. And during the formation of this lattice, other organic molecules like methane and carbon dioxide were trapped inside. They were enveloped by the water molecules like grapes, frozen inside a block of jelly. This structure is called a clathrate hydrate. This model, the dirty snowball model by Fred Whipple, shows that a comet's nucleus is not a uniform mixture. It is an icy matrix with organic compounds and rocky dust dispersed within. The first role of this water ice matrix was a protective one. Recall the billion-year journey of Atlas through interstellar space. It was constantly bombarded by high-energy cosmic rays. These cosmic bullets could easily break apart complex and fragile organic molecules, but they cannot penetrate too deeply. Just a few meters of outer water ice is enough to act as an extremely effective radiation shield. It absorbs and scatters the energy of the cosmic rays, completely protecting the precious molecules buried deep within the core. The water ice acted as a cocoon, a cryogenic prison preserving the comet's chemical legacy intact over unimaginable spans of time. The second role of water ice was a transport role. When Atlas neared the sun, it was the sublimation of water ice that was the main engine driving all activity. It released a tremendous amount of energy. As the water ice turned to vapor and erupted outward, it acted like an elevator carrying the heavier organic molecules and dust particles which could not escape on their own up from the surface and into the coma. Without the powerful sublimation of water ice, the organic cargo hold of Atlas would have remained locked inside, invisible to us. The water ice was the key that unlocked that treasure. And of course, besides water ice, there were other important ices: carbon dioxide, CO2 ice, or dry ice sublimates at a much lower temperature than water ice. The sublimation of CO2 is often the first sign of cometary activity as it enters from the cold regions of the solar system. It is the starter motor. Carbon monoxide CO ice, even more volatile, can be the main driver of activity at very great distances. The relative abundance of these ices can tell us a lot about the temperature of the region where the comet was formed. The presence of ammonia NH3 ice is also very important, as ammonia is a rich source of nitrogen, another essential element for amino acids and nucleobases. Data from the James Webb Space Telescope confirmed the presence of both water vapor and carbon dioxide in the coma of Atlas, further reinforcing the picture of a familiar but uniquely proportioned ice composition. So the cargo hold of Atlas was not just a list of molecules. It was a frozen chemical ecosystem, a water ice matrix acting as protector and transporter, and within that matrix, a treasure trove of other ices and a particular abundance of organic carbon compounds. Everything perfectly preserved, waiting for the moment to be released and join the dance of light. We have inventoried what we can see in the cargo hold of 3I Atlas, or at least infer from its byproducts. A treasure trove of simple hydrocarbons and familiar ices protected by a water ice matrix. But that is just the surface. That is what was released and broken apart by sunlight. What about what still lies hidden deep within the nucleus? Could there be even more complex, more important molecules for the story of life preserved in that cryogenic vault? This is where we enter the realm of unexplored potential. Detecting the most complex organic molecules in a comet from millions of kilometers away is an extremely big challenge. These molecules are often heavier, less volatile, and may only exist in very low concentrations. Their spectral signatures can be very weak and masked by the stronger signals from more abundant molecules like water or dicarbon. So the fact that we did not see them directly in Atlas does not mean they were not there. Based on what we have found in meteorites and in Comet 67P, it is entirely reasonable to speculate that Atlas also contained the most precious building blocks of life. Let's consider amino acids. The Murchison meteorite showed us that over 100 different types of amino acids can form naturally in space. The Rosetta mission confirmed the presence of glycine in Comet 67P. Given the organically rich formation environment of 3I Atlas, it is likely that its nucleus also contained a rich diversity of amino acids. These molecules, when delivered to an early Earth, would have provided the pre-made bricks for the first proteins to be assembled. They would have significantly accelerated the process of chemical evolution. Next, the nucleobases. These are the letters that make up the genetic code adenine, guanine, cytosine, thymine in DNA and uracil in RNA. Scientists have also found adenine and guanine along with other related molecules inside carbonaceous meteorites. If 3I Atlas also carried these molecules, it wasn't just delivering the bricks, but also the alphabet for life. Having these letters readily available, instead of having to create them from scratch in a chaotic soup, could have been a decisive turning point in the formation of the first self-replicating molecule. And what about lipids? These are fatty molecules with a water-loving head and a water-fearing tail. In a water environment, they have a magical ability. They spontaneously arrange themselves to form bubble membranes called lipid vesicles. These bubbles are the precursors to the cell membrane. The cell membrane is critically important. It creates a boundary, a separation between inside and outside, allowing the chemical reactions of life to take place in a controlled environment. Scientists have also found lipid-like molecules in meteorites. If Atlas also carried them, it wasn't just providing the ingredients, but also the first containers for the chemical factories of life. Amino acids, nucleobases, lipids, the bricks, the alphabet, and the containers. This is the holy trinity of prebiotic chemistry, and there is a very real possibility that the traveler 3I Atlas and its quadrillions of siblings are carrying all of them perfectly preserved in their icy cores. To confirm this with certainty, we would need future mission spacecraft that could fly close to an interstellar visitor, collect samples from its coma, and analyze them on the spot just as Rosetta did. But based on everything we already know, the hypothesis that the cargo hold of Atlas contains this unexplored potential is a strong scientific one. It was not just a carrier. It was a carrier of a complete starter kit. We have explored the incredible chemical cargo that a traveler like 3I Atlas might carry, not just simple organic molecules, but potentially the most precious building blocks of life itself. The idea of a Milky Way teeming with cosmic cedars, each carrying a starter kit for life, is an incredibly powerful and hopeful one. But the journey of these cedars is not easy. Interstellar space is not a gentle place. It is a harsh environment full of dangers that can destroy the very molecules they are trying to protect. Before the cargo can be delivered, it must survive the journey. Chapter 5. Surviving the journey. The biggest, most persistent, and most invisible enemy that an organic molecule faces in deep space is radiation. This radiation comes from two main sources, and both are relentless. Source number one is starlight. Although interstellar space is dark, it is not completely without light. The faint light from billions of stars in the Milky Way combines to form an interstellar radiation field. Most of this light is harmless, but it also contains high-energy ultraviolet UV photons emitted by hot young stars. As we know, these UV photons act as chemical scissors. If a complex organic molecule were floating freely in space, it would quickly be broken apart by a UV photon and destroyed. Source number two, and far more dangerous, are cosmic rays. This is not light. These are actual particles of matter, mostly protons, the nuclei of hydrogen and helium nuclei, that have been accelerated to near the speed of light. Their origin is still an area of research, but we believe they are created by some of the most energetic events in the universe: supernova explosions, rapidly spinning neutron stars, pulsars, and the supermassive black holes at the centers of galaxies. These particles are the bullets of the universe. They travel with terrifying energy. A single cosmic ray proton can have the same kinetic energy as a tennis ball flying at 100 kilometers per hour, all compressed into a subatomic particle. Our Milky Way is flooded with these cosmic rays, creating a constant high-energy rain that passes through everything in its path. When such a cosmic ray slams into an organic molecule, it destroys it completely. It doesn't just cut a bond, it disintegrates the entire structure. Life on Earth is protected from this deadly rain by two layers of shielding our planet's magnetic field and its thick atmosphere. But a comet drifting in interstellar space has no such luxury. It must face the storm head-on. So how can fragile organic molecules possibly survive billions of years of constant bombardment? The answer lies in the strength of collective shielding. A single molecule stands no chance, but a molecule buried deep inside a kilometer-wide iceberg is another story. A comet is by its very nature a natural radiation shelter. Let's consider the UV photons. They can penetrate a very thin layer of material, but they cannot pass through rock and ice. A layer of dust and ice just a few micrometers thick on the surface is enough to completely block the UV light, protecting everything underneath. Cosmic rays are much more powerful. They can penetrate meters of material, but even they have their limits. When a cosmic ray slams into the icy surface of the comet, it collides with the water atoms and loses energy. It creates a shower of secondary particles, but their energy is absorbed and scattered within the first few meters of ice. Calculations show that any organic molecule buried deeper than about 5 to 10 meters below the surface of a cometary nucleus would be almost completely shielded from the ravages of cosmic rays. They are in a safe zone, a frozen cocoon where time seems to stop and the energy storms of the universe cannot reach. The nucleus of 3I Atlas, with its kilometer-scale diameter, was a nearly impenetrable fortress against radiation. So while its surface may have been baked and transformed into a dark tholin crust, its core remained pristine, a primordial chemical treasure perfectly preserved, waiting. We have identified the main enemy of the interstellar journey, a relentless rain of high-energy radiation, from ultraviolet photons to powerful cosmic rays. Any organic molecule directly exposed to this storm would be destroyed. So how can the fragile chemical seeds survive a journey of billions of years? How did 3I Atlas arrive at our solar system still carrying a rich organic cargo? The answer lies not in the strength of individual molecules, but in the strength of the collective. The answer lies in the very structure of the ship that transported them. The cometary nucleus. The nucleus of a comet like 3I Atlas is not a solid rock. It is a porous collection of ice and dust held together by its own weak gravity. But for the organic molecules buried deep inside this structure is a nearly impenetrable fortress. Let's look at how this icy armor works against the two main types of radiation. Shield layer 1 against ultraviolet UV rays. UV photons from starlight, although energetic, do not have strong penetrating power. They are easily blocked by matter. A layer of dust and ice just a few micrometers thick, thinner than a human hair on the surface of the comet, is enough to completely absorb the UV photons, preventing them from reaching deeper inside. So while the very outer surface layer might be chemically altered just a little below the surface, the molecules are completely safe from this enemy. The anti-UV armor is extremely effective. Shield layer 2 against cosmic rays. This is a much bigger challenge. Cosmic rays are extremely high-energy subatomic particles. They can penetrate meters of solid matter. When a cosmic ray, for example, a high-speed proton, slams into the icy surface of the comet, a series of events occurs. It will collide with the nucleus of a water atom, shattering that nucleus and creating a shower of secondary particles like neutrons, pions, and muons. These secondary particles then go on to collide with other atoms, creating even more particles. This process is like throwing a billiard ball into a pre-stacked pyramid. A single impact can cause a chain reaction that collapses the entire pyramid. However, with each collision, the energy of the particles is dispersed. This particle shower, though powerful at first, quickly loses its energy as it travels deeper into the ice. The water molecules in the ice act as trillions of tiny sacrificial targets, absorbing and slowing down the incoming particles. Scientists have performed detailed computer simulations to calculate how deep cosmic rays can penetrate. The results are clear. Most of the energy of a cosmic ray shower is completely absorbed within the first few meters of ice. This means that any organic molecule buried deeper than about 5 to 10 meters below the surface of a cometary nucleus would be almost completely shielded from the ravages of cosmic rays. They are in a safe zone, a chemical sanctuary, a frozen cocoon where time seems to stop and the most violent energy storms of the universe cannot reach. The nucleus of 3I Atlas, with its kilometer-scale diameter, was a nearly impenetrable fortress against radiation. Only the very outer crust, a few meters thick, was affected. The vast core inside, making up over 99% of its mass, remained pristine, perfectly preserving its chemical legacy from the moment of its formation. It's like a peach. The outer skin may get tanned and hardened by the sun, but the sweet flesh inside remains protected. A comet is not just a carrier, it is an armored cryogenic vault. It is this simple yet effective structure that has allowed fragile chemical seeds to survive unimaginable journeys over time spans longer than the age of our own planet. We have seen how the icy matrix of a cometary nucleus acts as an effective radiation shield, protecting the precious chemical cargo deep inside. But the story of survival doesn't end with passive defense. The very relentless attack of radiation inadvertently creates an additional layer of armor, a cosmic skin formed from the very scars of the journey. This is the story of the dual role of destruction and creation, the story of the Tholen crust. Let's focus on the outermost few meters of the cometary nucleus, the war zone, where cosmic radiation can penetrate. In this region, cosmic rays and high-energy UV photons are constantly bombarding simple ice molecules like water, methane, and ammonia. As we know, this process, called radiation processing, breaks chemical bonds. But it doesn't just destroy. The molecular fragments, the highly reactive free radicals, don't just disappear. They immediately look for other things to bond with, to recombine into new, more stable structures. And in this high-energy chemical soup, carbon atoms play a central role. They bond with each other and with other atoms, forming longer and more complex chains. Over millions and billions of years, this constant process of breaking and recombining has created an entirely new layer of material on the comet's surface. That material is no longer pure ice. It is a complex, sticky, carbon-rich mixture of large organic molecules collectively known as tholins. The word tholin was coined by the astronomer Carl Sagan from an ancient Greek word meaning muddy or hazy, a very fitting name. Tholins are not a single molecule. They are a kind of cosmic asphalt, a collection of complex organic polymers. And they have a very important characteristic. They are dark, very dark, usually a deep red-brown or almost black color. This tholin crust is the explanation for the mysterious dark red color of Oumuamua, and also the reason why the nuclei of most comets are blacker than coal, even though they are mostly made of ice. The surface of 3I Atlas before it awoke was undoubtedly also covered in such a crust, and this crust has an extremely important dual role. Role number 1, a product of destruction. The tholin crust is a piece of evidence, a scar of the relentless attack of radiation. It is created from the very destruction of the original ice molecules. It is a reminder of the harshness of interstellar space, but it is also a beautiful example of chemical resilience. From chaos and destruction, a new complexity, a new order has emerged. Role number 2, an additional protective layer. This dark tholin crust, once formed, acts as an additional suit of armor, a cosmic sunscreen. It is very good at absorbing UV photons, preventing them from penetrating deeper and destroying the pristine ice below. It can also slow down the sublimation of the ice when the comet passes through slightly warmer regions of space. It acts as an insulating layer, so the radiation is both the attacker and the creator of the protector. A subtle feedback loop. Furthermore, this tholin crust is not just an inert shield. When a comet like Atlas eventually does impact a planet and release its material, this tholin crust will also be sewn into the primordial oceans. And when these complex tholin molecules come into contact with liquid water, they can be hydrolyzed, breaking back down into simpler organic molecules, including amino acids. Some scientists even believe that this tholin crust could be an even more important source of the building blocks of life than what is preserved inside the ice. So the armor forged during the journey could end up being one of the most precious gifts upon arrival. Our traveler has survived an unimaginable journey, encased in an armor of ice and an organic crust. Its chemical cargo hold has been protected from the harshness of interstellar space. But the final and most violent challenge still lies ahead. Transporting the cargo to the destination is one thing, but delivering it safely is another story entirely. To sow its chemical seeds, the comet must pass through the final obstacle, a planet's atmosphere, an invisible wall of fire. Chapter 6. The Final Descent. Let's imagine a scenario in Earth's distant past. An interstellar comet, much like 3I Atlas, after its long journey, happens to be on a collision course with our planet. It is approaching at a terrifying speed. The velocity of interstellar objects is often higher than that of solar system objects, reaching up to 50, 60, or even 70 kilometers per second. Tens of times faster than a speeding bullet. As it hits the outermost layers of the atmosphere at an altitude of a few hundred kilometers, almost nothing happens. The air there is too thin, but as it plunges deeper, the air becomes exponentially denser, and one of the most powerful physical processes in nature begins to take place: adiabatic compression. The comet is moving so fast that the air in front of it doesn't have time to get out of the way. Instead, it gets extremely compressed, creating a shock wave in front. Compressing a gas rapidly causes its temperature to skyrocket. This is the same principle that ignites the fuel in a diesel engine. The air directly in front of the comet can be heated to temperatures of thousands or even tens of thousands of degrees Celsius, hotter than the surface of the sun. It is important to understand the comet is not burning up from friction with the air in the way we usually think. It is being melted and vaporized by the superheated ball of plasma it creates in front of itself. The entire icy nucleus begins to sublimate violently. The outer layers of ice and rock are stripped away, leaving a brilliant streak across the sky. A shooting star, but on a completely different scale. This fireball can be brighter than the sun for a few seconds, visible even in broad daylight. At the same time, the immense pressure from the shockwave acts on the comet's structure. Imagine facing a hypersonic hurricane. This pressure, called ram pressure, is enormous. Now remember that comets are not solid rocks. They are porous collections of ice and dust loosely held together. They have very low structural integrity, possibly weaker than a block of packed snow. Faced with such enormous pressure, they cannot hold their shape. The danger here is clear. If the comet is too small, it will completely vaporize at a high altitude like most meteors. Its chemical cargo will be destroyed by the extreme heat. If the comet is too large and too solid, more like an iron asteroid, it might survive its passage through the atmosphere and impact the surface. Such an impact would create a giant crater, releasing an amount of energy equivalent to millions of nuclear bombs. The heat of the explosion would again destroy most of the organic molecules. Both of these scenarios are terrible delivery methods for fragile organic molecules. The survival of the chemical seeds seems impossible in the face of the atmospheric wall of fire. So is there another scenario? A middle path that allows the cargo to be delivered more gently? The answer may lie in the very weakness of the comet itself. We are faced with a paradox. A comet, the perfect carrier for organic molecules through the harshness of space, seems to fail at the final step. The atmospheric wall of fire appears to be an insurmountable obstacle, capable of incinerating or blasting apart the entire precious cargo. But what if the very weakness of the comet, its lack of structural integrity, is the key to the survival of its chemical seeds? What if the best way to get through a wall is not to punch through it, but to break apart before you even hit it? This is the scenario of redemptive fragmentation. Remember that a comet's nucleus is not a monolithic rock. It is a loose collection of ice and dust held together by its own weak gravity. Its structure can be very porous, like a block of packed snow or a frozen sponge. It is full of cracks, voids, and structural weaknesses. When such a fragile object plunges into the atmosphere at hypersonic speeds, the enormous ram pressure acts upon it. There will come a point where the aerodynamic pressure exceeds the object's own tensile strength, and at that moment, it will shatter. it won't just break into 2 or 3 pieces. It will undergo a process called catastrophic fragmentation, breaking up into thousands, millions of smaller fragments in an extremely violent airburst. We have a perfect example of such an event in modern history, the Tunguska event of 1908. On a June morning, a huge explosion estimated to be equivalent to 15 megatons of TNT, over 1,000 times more powerful than the atomic bomb at Hiroshima, occurred over a remote forest region in Siberia. The blast flattened over 2,000 square kilometers of forest, knocking down some 80 million trees. Its shock wave traveled around the Earth twice. But here's the strange thing: no impact crater was ever found. Today, scientists believe the culprit was most likely a small asteroid or a comet fragment about 50 to 60 meters in diameter that exploded at an altitude of about 5 to 10 kilometers above the ground. It did not impact, it detonated in the air. The Tunguska event shows us something important. An impactor does not have to reach the ground to release its energy. And for a comet with its weak structure, such an airburst is an almost inevitable outcome. So what does this mean for the delivery of organic molecules? It changes everything. Instead of a single concentrated impact releasing a super high temperature fireball at one point, we have an airburst. This explosion still releases an enormous amount of energy and creates a violent shock wave, but it happens high up in the atmosphere. The cometary nucleus is turned into a giant cloud of water vapor gas and trillions of tiny dust particles and ice fragments. This cloud, with its huge surface area, will be rapidly decelerated by the atmosphere. It will lose the bulk of its terrifying speed. And this is where the redemption happens. The small dust particles and ice fragments, now moving much more slowly, will no longer create searing plasma fireballs. Instead, they will slowly fall through the lower layers of the atmosphere. This process, called atmospheric deposition, could take months or even years. And during this slow descent, the temperatures they endure are much, much lower. The complex organic molecules protected inside the dust grains or small ice fragments have a much higher chance of survival. The catastrophic fragmentation, an event that seems like total destruction, is actually an extremely effective breaking and dispersal mechanism. It has turned a single deadly bullet into a gentle rain of dust, and that very rain is the perfect delivery method. The catastrophic fragmentation of the comet in the upper atmosphere was not an end. It was a transformation. It turned a single violent object into a vast, diffuse cloud. And from that cloud, a new, much slower and gentler process began. Not a landing, but a settling. This is the final step in the journey of the chemical seeds, the rain of life. After the airburst, the atmosphere of the early Earth would have been filled with a huge amount of cometary material. The water vapor would condense and form clouds. Other gases would mix into the atmosphere, and most importantly, there were the quadrillions of organic dust particles and tiny ice fragments. These particles, now having lost most of their initial velocity, would no longer fall like bullets. They would begin a long, slow journey drifting down through the lower atmospheric layers under the influence of gravity and air currents. Some larger particles might still create small shooting stars as they entered the denser layers of air, but the micrometer-sized particles, the carbonaceous dust grains, were small enough to be effectively decelerated without burning up. They would reach a terminal velocity and slowly fall like particles of soot in the air. The final descent of these chemical seeds was not an explosion, but a rain. A black rain lasting for months, years, or even decades after the initial impact event. The sky of the early Earth might have darkened as these organic dust particles slowly settled, blanketing the entire planet in a thin veil. And where did they fall? They fell into the churning primordial oceans. And this is where the seeding process truly took place. These dust particles carrying amino acids, nucleobases, and other complex organic molecules dissolved into the water. They enriched the primordial soup with high-quality pre-made ingredients from a cosmic chemical factory. Instead of having to start from simple inorganic molecules, the chemical reactions in the ocean now had a starter kit, a rich supply of more complex building blocks. This event would not have happened just once. During the late heavy bombardment, the Earth was constantly being assaulted by comets and asteroids. Each airburst was a new seeding event. Over hundreds of millions of years, the Earth's oceans could have accumulated a vast amount of extraterrestrial organic material. So the gentle delivery scenario is complete. Survival of the journey, ensured by the icy armor of the nucleus. Survival of the landing ensured by catastrophic fragmentation in the airburst. Distribution ensured by a global dust rain seeding the molecules into the liquid environment of the oceans. The journey of the chemical seeds from a distant lost home across the interstellar ocean and finally to a new world has come to an end. They have been delivered safely. And now, in the warm, nutrient-rich oceans of the early Earth, a new, even more wonderful story was ready to begin. The story of life itself. We have followed the chemical seeds on an extraordinary journey, from their formation in a distant cradle to their survival across the interstellar ocean, and finally to their gentle descent as a dusty rain seeding the oceans of a young Earth. The scientific story has been fascinating, but the implications behind it, the philosophical meanings, are even more profound. The chemical panspermia hypothesis, strengthened by the existence of travelers like 3I Atlas, completely changes how we see our own origins and our place in the cosmos. Before we go further, a critically important distinction must be made. The title of this chapter, Are We All Aliens?, is a provocative question, but it needs to be understood correctly. The chemical panspermia hypothesis does not say that our life came from elsewhere. It does not suggest that the first microbes traveled from Mars or from another star system to Earth. That is a different idea. Lithopanspermia, a fascinating but currently evidence-poor hypothesis. Instead, chemical panspermia only says that our ingredients, the complex organic molecules, the building blocks of life, came from space. This is a subtle but critically important difference. It means that the final and most mysterious leap, the leap from complex chemistry to self-replicating biology, from inanimate molecules to the first living cell, very likely still happened right here on Earth. The Earth is still the cradle of life, but chemical panspermia suggests that the cradle was supplied with the best materials imported from all over the galaxy. We are not aliens in a biological sense, but we are aliens in a chemical sense. Every carbon atom, every amino acid molecule in our bodies could carry with it a cosmic history, a story of a lost home. This distinction has an extremely profound implication. It implies that prebiotic chemistry, the process of forming the building blocks of life, is not a special event that happened on one lucky planet. It is a universal galactic phenomenon. Imagine this. Stars in their cores are factories for heavy elements like carbon and oxygen. Supernova explosions seed these elements throughout the interstellar gas clouds. Inside those cold gas clouds, complex organic chemistry begins to happen naturally. As new star systems form, these molecules are incorporated into comets and asteroids, and then dynamical instabilities eject these carriers throughout the galaxy, creating a global distribution network. Our Milky Way, from this perspective, is like a giant ecosystem constantly recycling and distributing the components of life. It is not a collection of isolated oases. It is a single ocean with chemical currents flowing ceaselessly. This means that the primordial soup was not something unique to Earth. Every rocky planet and every star system in the right place likely received the same rain of organic molecules. They all received the same starter kit. The chemistry of life is not a miracle. It is a cosmic standard. This does not diminish the specialness of life on Earth. On the contrary, it places that specialness in a new context. Our specialness may not lie in having unique bricks, but in the fact that on this planet, those bricks found a master builder, a great architect, the process of evolution to assemble them into such a complex and beautiful structure. Our common origin, according to this hypothesis, is not a single cell on Earth. Our common origin is the chemistry of the Milky Way itself. We have just arrived at a revolutionary idea. Prebiotic chemistry is a universal galactic phenomenon. The Milky Way doesn't just create stars and planets. It constantly produces and distributes the basic building blocks of life. Every potential world, every new Earth out there is receiving the same starter kit delivered by icy travelers like 3I Atlas. This leads us to one of the most profound and fascinating speculative questions in science. If the ingredients are available everywhere, is life itself an inevitability? For centuries, we have tended to view life on Earth as an extraordinary stroke of luck, an almost unrepeatable accident. A lightning bolt striking a puddle at just the right time with just the right chemicals under just the right conditions. The probability of it seemed incredibly low. This view, known as the rare Earth hypothesis, suggests that the combination of countless lucky factors, from having a giant planet like Jupiter for protection to having a large moon to stabilize our axis to plate tectonics, has made Earth a unique oasis in a largely sterile universe. From this perspective, we may be the only intelligent beings, or even the only living things in the entire galaxy. But the chemical panspermia hypothesis, strengthened by observations of interstellar visitors, offers a completely different perspective. It suggests that at least one of those lucky factors, the presence of complex organic molecules, was not lucky at all. It was the standard. If rocky planets in habitable zones throughout the galaxy are being constantly seeded by the same chemical rain, then the primordial soup is not a rare dish. It's the standard menu. This completely changes the probability calculation. Some scientists, like the biochemist Nick Lane, go even further. They argue that once you have the basic ingredients, liquid water, organic molecules, and a sustained energy gradient, like at hydrothermal vents, the emergence of primitive metabolic processes and ultimately life may not be an accident. It could be a deterministic consequence of thermodynamics. Think about this. The universe always tends to go from order to disorder, a law known as entropy. But life seems to go against that. It creates order from chaos. However, on a larger scale, life is an extremely efficient machine for creating disorder. It takes high-order energy sunlight and turns it into low-order thermal energy waste heat. It is a fantastic tool for increasing the entropy of the universe. From this perspective, life could be the universe's solution to a physical problem. It is the most efficient way to dissipate the energy gradient on a wet, sunlit planet. If this is true, then the emergence of life, given the right ingredients and conditions, may not be a rare event, but a common, almost inevitable process, like water freezing when it gets cold, or an apple falling to the ground. It could be a potential fourth law of the universe, a natural tendency of matter to self-organize into ever more complex structures to dissipate energy more efficiently. Of course, this is still a realm of deep speculation. We still do not fully understand the leap from chemistry to biology, but the idea of chemical panspermia of a galaxy seeding itself has provided a solid physical basis for these speculations. It makes the question, is there life out there, seem much more plausible. If the seeds are everywhere, and if the fertile gardens are also everywhere, then why would we think our garden is the only one in which flowers have bloomed? 3i Atlas with its organic cargo hold did not give us the final answer, but it brought us hope, a hope built on a foundation of chemistry. The idea of a bio-friendly universe where chemical seeds are everywhere and their germination may be an inevitability is one of the most transformative ideas modern science has to offer. It changes our story. From a story of loneliness in an empty universe to a story of connection in a chemically vibrant galaxy. And to end this chapter, we must return to the traveler that inspired this journey. We must look again at 3i Atlas, not just as a comet, but as a symbol for the legacy of the exiles. We began the story of Atlas as a tragedy, an object exiled from its home, cast out on a long and lonely journey through the darkness. But the chemical panspermia hypothesis allows us to look at that story in a completely new light. Perhaps it was not a tragedy. Perhaps it was a mission. Not a conscious mission, of course, but a mission entrusted to it by the very laws of the universe. Three-Eye Atlas and the quadrillions of other exiles drifting in the sea between the stars may not be just inanimate icebergs. They may be the gardeners of the galaxy. Imagine this. Every star system is a garden where complex chemical plants are growing. And every period of instability, every chaotic dance of the planets acts like a strong wind, blowing the seeds from this garden far and wide. Most of those seeds will fall on barren ground, empty space, or unsuitable planets. But occasionally, one of them will happen to fall on a fertile patch of soil, a young rocky planet in the habitable zone with oceans of liquid water. And there that chemical seed will be sown. From this perspective, the violent events, the gravitational ejections we have described, are not acts of destruction. They are acts of planting. The universe, through these seemingly chaotic mechanisms, is actively spreading the potential for complexity. It is ensuring that no star system is left behind, that every potential world has the chance to receive the necessary building blocks. Three-Eye Atlas. The traveler we have followed was one of those gardeners. It did not just carry the memory of a lost home, it carried the potential for future homes. Its organic cargo hold was not just a chemical legacy. It was a starter kit, a promise of complexity. As it swept through our solar system, it was not just a beautiful sight. It was a reminder that the very carbon atoms in our bodies may have once taken a similar journey. The final legacy of the exiles is a legacy of connection. It blurs the boundaries between star systems. It shows that we are all part of a larger story, a chemical story that spans billions of years and stretches across 100,000 light years. We may be made from the same stardust seeded by the same kinds of comets and share a common chemical ancestry with any other life that might exist out there. It is an idea that brings both humility and grandeur. Humility because it shows we are not the center. And grandeur because it shows we are part of something truly universal. We have come a long way. A journey that began with the most fundamental question, where do we come from? And that question has led us from the primordial oceans of a young Earth out to the asteroid belts, to distant comets, and finally across the ocean between the stars. In this final chapter, before we let our minds rest, let us look back at the path we have traveled. Let's string together all the clues, all the ideas, to see the big picture they paint together. This is a summary of the story of the wandering seeds and their legacy. Chapter 8, Children of the Stars and Conclusion. Our journey began with the mystery of origin. We confronted the vast gap between a sterile rock and a living cell. We explored the two main possibilities: abiogenesis, life sprouting from the materials available at home, and panspermia, the idea of seeds sown from space. We chose to focus on the chemical panspermia version, the hypothesis of the transport of the building blocks of life, not life itself. Next, we searched for evidence in our own backyard. The story of the Murchison meteorite gave us a letter written in stone proving that over 100 different types of amino acids can form naturally in the asteroid belt. The historic Rosetta mission to Comet 67P confirmed that comets are also rich chemical reservoirs carrying both the amino acid glycine and phosphorus, a key component of DNA. Finally, the isotopic analysis of water showed that our oceans are most likely a mixture delivered by both asteroids and comets. The evidence was clear: our solar system is teeming with the ingredients of life. With that foundation, we built the bridge between the stars. Based on the Copernican principle, we argued that if prebiotic chemistry happens here, it must happen everywhere. We envisioned the Milky Way as a sea of exiles, with quadrillions of comets and asteroids ejected from their homelands, forming a galaxy-wide transport network. And we introduced 3I Atlas as a perfect example, a confirmed interstellar carrier with a rich organic cargo hold. Then, we opened the organic cargo hold of Atlas. By inferring from the blue smoke of dicarbon, we discovered the fire within an abundance of organic parent molecules like methane and acetylene. We also discussed the crucial role of the water-ice matrix, not just as a component, but as a protector, a shield. And we speculated on the unexplored potential, the possibility that it also contained the most precious building blocks, like amino acids and nucleobases. But could that cargo survive the journey? We confronted the enemies of space. We saw that radiation from UV rays to cosmic rays is a lethal threat. But we also discovered the shields, the icy armor of the nucleus, thick enough to protect the pristine core and the dark organic tholin crust, a skin forged from the very scars of the journey. Finally, we considered the final descent. We faced the wall of fire of the atmosphere, a seemingly insurmountable challenge. But then we found a solution in the comet's own weakness, redemptive fragmentation. An airburst like the Tunguska event turned a single bullet into a rain of life, a gentle organic dust that seeded the primordial oceans. And from there, we contemplated the deeper implications. We asked, are we all aliens? We clarified that we are speaking of a common chemical, not biological origin. This implies that prebiotic chemistry is a universal phenomenon. And if the bricks are everywhere, is life itself an inevitability, a natural consequence of thermodynamics? We looked back at the legacy of the exiles, the gardeners of the galaxy, carrying the potential for life to new worlds. The entire journey from a simple question has led us to a new vision of the universe, a vision of connection, of universality, and of infinite potential. We have come a long way, from the mystery of the origin of life on a barren earth to the evidence etched in rocks that fell from the sky and in distant snowballs. We have built a bridge between the stars, envisioning a sea of exiles. And we have seen that travelers like 3I Atlas are not just inanimate icebergs, but potential sowers, the gardeners of the galaxy. This entire journey leads us to one final conclusion, an idea that is not just scientific, but deeply philosophical and personal, an idea that changes how we see ourselves. Take a moment to truly contemplate this. If the chemical panspermia hypothesis is correct, even in part, it means that we are in a very direct and tangible way, the children of the stars. Every single carbon atom in your body, the atom that is making up your skin cells, the neurons in your brain, and the very DNA molecule that carries your identity, has an extraordinary cosmic history. It was not born on Earth. It was forged in the molten core of a massive star that lived and died long before our sun was formed. Then it was flung out into space in a brilliant supernova explosion, traveling through the darkness for millions of years as part of a cloud of gas and dust. From that cloud, a new star system was born, perhaps a distant red dwarf system. There, those carbon atoms combined with other atoms to form complex organic molecules. And then they were trapped inside a chunk of ice, a comet, much like 3I Atlas. That iceberg, after millions of years of peace, was ejected from its home in a chaotic dance of planets, beginning a new journey of exile through the interstellar ocean. It traveled through the darkness for hundreds of millions, even billions of years, protected by an icy armor carrying its precious chemical legacy. And then, by a cosmic coincidence, its path intersected with a young forming star system called the Solar System. plunged into the atmosphere of a third rocky planet, a planet with oceans of liquid water. It disintegrated in an airburst, and those carbon atoms, those organic molecules, slowly fell as a black rain seeding the primordial oceans. From there, in that enriched soup, a new story began. A story of self-replication, of evolution, of ever-increasing complexity. And after 4 billion years, those carbon atoms are now here. They are a part of you. You do not just look out at the stars. You are made of them and of the travelers that journeyed between them. The history of the universe is not a story that happened somewhere far away. It is written in your very DNA. You are a living library carrying the memory of dead stars and interstellar journeys. You are a manifestation of cosmic connection. Thank you for joining Cosmic Drift on this journey to explore these wandering seeds. Thank you for taking the time to contemplate our deepest origins. As you fall asleep tonight, feel that connection. Feel that you are not an isolated being, but a part of a vast and ancient cosmic network. Let the idea that you are made of stardust bring you not a sense of smallness, but a sense of belonging. You belong here. You belong to the universe. I wish you a truly peaceful night. And sweet dreams of your stellar homelands.